Welcome to this video. In this one, we're going to go over circuits that have a mixture of series and parallel within one circuit. Okay, so we're going to start off in ones that are easy and pretty straightforward. Then we're going to move on ones that are a little more difficult and will involve switches. If you want to follow along, just get a blank piece of paper. It's always good to have a calculator and a pencil, and probably good to also have an eraser. Okay, so let's get into it. The first question is asking the voltage between Y and Z in the circuit. So when we look at this portion of the circuit, Y and Z, we see that we'd just be dealing with these three resistors that are wired in parallel. We also have some information where it says each of the 6 ohm loads is 2 amps. Okay, so each one of those. Now we know that we're only dealing with this section with the resistors wired in parallel. We also know we're solving for voltage, and we do know the current of each one, and we also have the ohms of each of the resistors, so the resistance of each of the resistors. Okay, because in this portion we're only dealing with a parallel circuit, I like to draw a P so I can label this that I'm dealing with a parallel circuit here, and then I'm going to write down what I have. So I'm first going to label the question in simple terms. I want voltage, so I'm just going to call that E with a question mark. Underline that, that's what I'm looking for. And I do have R, those resistances, and I also know my current, at least of each of the separate ones. But with this, I'd be able to find the total. Okay, so we're dealing with a parallel circuit, so we need to understand that when we have currents in each of our resistors, each of those currents will add together to equal the total current. So because of this, we already know that each of these 6 ohm loads is 2 amps. In other words, these 6 ohm resistors each have 2 amps of current going through them. And with a parallel circuit, we're going to add the amps to get our total amperage. So we're going to do 2 plus 2 plus 2. I'm going to do a calculator for most numbers, but I think that I don't need to do a calculator for this. Okay, so we have 6, and that would be known as the I total, or the current total, the amperage total. Okay, so I like to circle answers that aren't my final answer, and then my final answer I like to put a square around. That's what I personally do. Okay, so that's my I total there. And now I also need to find my R total if I want to find my voltage. And this is because we need to remember the formula E equals I times R. We can write this as E, and then we can write I times R below it. And this way, with this method, no matter what we're looking for, we can cover what we're looking for. In this case, we're looking for the E. We know it's I times R. If let's say we're looking for the R, then we'd see E over I. And if we're looking for the I, we'd see E over R. Okay, so now to find the R total, we're dealing with a parallel circuit. So like I taught in my series versus parallel circuit video, to find the total resistance of a parallel circuit, you have to do a kind of funny formula. I talk about it in that other video. We're going to plug in the numbers so you'll see it in real time here. So what we do is we know each of the resistances of each of the resistors. In this case, they're all the same. A lot of times they won't be, but this is pretty easy here. So we have 6 ohms on each of the 3 resistors. So to find the total resistance, we're going to do 1 over 6 plus 1 over 6 plus 1 over 6. We're going to equal that to a total number, and then we're going to do 1 over that total number, and that will equal our R total. Okay? Again, I have a video explaining all of this. Okay, so now I pull out a calculator for anything that's not incredibly simple, because it's easy to make mistakes. So there should be less mistakes when using a calculator. So we're going to do 1 over 6, and we're going to get 0.16 repeating. Make sure to write down that it's 0.16 repeating. That is good information. So we have 0.16 repeating. I always like to double check. It's kind of funny. You know, I'd do it quickly in real life. But then you're going to add that together 3 times. And do not multiply it by 3, because most of the time these will be different numbers. So it's just not a good method to think about multiplying. Rather just add them up every time. Unless you have like 10 of the same resistors have the same resistance. Okay, maybe. But you should always just add them. It's a sure method. Okay, so we're going to do 0.16 plus 0.16 plus 0.16. I'll make that better. I'll make sure I look before I do that. Okay, so we get 0.48. You could probably do that in your head, but that's not the point here. Trying to get the correct answer with no mistakes. So 0.48, there we go. And now remember, that's not our final answer. That is the total that we're going to do 1 over to get our actual resistance total. So I shouldn't have squared that, my bad. Or put a square around it. Okay, so we see 1 over 0.48. We're going to equal that. We're going to get 2.083. And remember, make sure to write down the fact that it is 0.083 repeating. Okay, so that little line above the 3. And this is because sometimes to get closer to your accurate answer, you're actually going to have to write as many 3's as possible, and that will get you closer to the accurate answer. And a lot of times you'll just have to do 1 of them or maybe 2. Okay, and with time you will learn the scenarios where you're probably going to want to use either which of those methods. Okay, but remember the question in the beginning, what I was asking was we want the voltage. Okay, so now we have the resistance total and we also have the current total. It's also good to note that the resistance total is 2.083, so we might just use the number 2. Realistically, we're probably just going to use a whole number 2. Okay, now we just need to think that E equals I times R, so we can plug in those numbers. We have I, we have 6 times R, we have 2, we're just going to go with 2, and that will equal 12. That will equal the E total for that section of the circuit that we were going over, where we had Y to Z. Okay, so there's the final answer, 12 volts from Y to Z on this circuit. So as we can see, this started with a mixture circuit, but we didn't solve for both of them yet. We were just figuring out that, okay, when we have a mixture of them and we only want to figure out a section that is, let's say, only wired in parallel, then we only have to solve for that section, thinking all in terms of a parallel circuit. While things are a little different if, let's say, we want to go from X to Z, but we will build up to that. Okay, so now if you're wondering about that EIR, I have 4 of those that will tell you every Ohm's law formula. So that's what these T's are here. I'm just going to make this quick, but this is what helps me. I actually memorized this, but if you write this down enough times, you will memorize it. So let's write it down. I'll put it on a flashcard, because this is maybe what you'll do in the beginning. There's a few different ways to memorize this, but I find like a funny saying or something is always the best way for me to remember things. Whether I'm trying to remember the strings on my guitar, or I'm trying to learn Ohm's law formulas, a funny saying is probably the best way for me to remember it. And then after, I'm also going to give you another tip that'll help you remember these in a different way. Okay, so I'll just go to a blank page for a second so there's no distractions. All the energy is on this. Okay, so we're going to think of a friend named Epe. And it's not just Epe, it's Epe squared. I don't know how else to remember that. I just say, I know a guy, his name's Epe squared. Okay? That's his name. Epe squared is a very interesting person. He likes to eat ear pie. I don't know why he likes that, but he also does not spell ear how you normally would. It's E-I-R. Okay, so you see the formula, E equals I times R. We also see the power, Ohm's law formula, of P equals I times E, current times volts. Epe squared also has a friend named Peter. Peter spells his name P-I squared R. So the I is like Pete, help me remember it, Peter, P-I squared R. Just say it a bunch of times, you'll remember it. Peter always says, I have to pee. He always has to pee. And after he pees, just like we all do sometimes, he gets the shivers. He goes, rrr. Okay? I know it's kind of weird, but this is how I was taught it, and I never forgot it. So there you go. So one more time. We know a guy, Epe squared. He likes to eat ear pie. He knows a guy named Peter, P-I squared R. Okay? He's always saying, I have to pee, after he pees. Okay? Now you know every single Ohm's law formula. Like if you get one of those ugly books or anything that has the circle on with all the formulas, you can make every formula with this. Okay, so I have a whole video over this, so I don't want to spend too much time over this, but I'll show you the simple method, and then I'll go over the ones with squares, because those are kind of weird. So you look at what you're solving for, and this might seem kind of elementary, but this is how you're going to learn in the beginning. You just cover what you want to solve for. So here, let's say I want to do voltage, I want to do E. Now I see I times R. When it's separated by that line, it's next to each other, that's multiplied. And I know I already did this, but I'll go over one more time. If you cover the I, that's E over R, because anytime that line's there, that's like saying this is over that. If I want to do R, that is E over I, because that's how you do it for all of them. And obviously, let's say I wanted R here, in this case with the square. Okay, that's just P over I squared. It's not too difficult. The weird thing is, what if I wanted to solve for I squared, and that's P over R? Okay, so because I squared equals P over R, then whatever P over R equals, we're going to have to square root it. Because when we square root it, that's going to be the number that when it is squared equals P over R. You see, they equal each other. So similarly, if I wanted E squared, and I was doing P and R, let's say I had power and resistance, and I wanted to find my voltage, well then I'd have to solve with E squared in the beginning. So then I'd have E squared equals P times R. So basically the same thing. All that it's saying is that when I multiply P times R, that number is going to equal something that's squared. So for this number to be squared, we have to square root it when we actually want to find our answer. So E squared equals P times R, therefore P times R, that total number is going to be square rooted to create this E squared number. Okay, so you could always write each of these down in the beginning, and then any time that you want to use it for any of these problems, you can just pull out this flashcard. But after you do this multiple times, you're going to want to get to a point to where you either have it memorized or you practice to memorize it. And it's not all that difficult. One thing that can help you is a different method of remembering each one. Like I was saying, you had ear and pi, so how I think of each of them is the number at the top and then the two numbers on the bottom. And that's how I remember each of these names. So I have the ear, pi, and I even said the Peter, the pi squared r, and the last one was E squared over P times R. So I just remember Eper. I couldn't think of anything else, but I was thinking, how could I remember it? And Eper, kind of like keeper, but it's Eep with the two E's because it's E squared. So that's how I remember it. Eper, E-E-P-R. Okay? Okay, so now the next question. What is the wattage of the 10 ohm load? So now we just want to know this 10 ohm load, and we solve for some things already with our parallel section of the circuit. So now we have a question asking about the series portion of the circuit without any other additional information, besides the fact that we have this 10 ohm resistor. Okay, so now this is the beginning to the section where we're going to understand what happens when you wire these series and parallel circuits together. And for one thing, it's good to actually visualize it, so it's good that we have this schematic here. So let's just back up a second, remember what we did. We had each of these resistors that had these 6 ohm loads. So each of these 6 ohm loads has 2 amps in this parallel section of the circuit. So we know the current going through each of the separate resistors wired in parallel, but we also solved for the total current in order to figure out our last answer. We can also visualize the fact that our circuit starts with a resistor in series, and then after that it goes to a section of 3 resistors wired in parallel. So now that we know the total current for the parallel section of the circuit, we know that this whole section is going to be 6 amps, okay? Because we solved for that already. We also know when a resistor is wired in series to another resistor, it has the same amps. So because we know that this section of these resistors wired in parallel is 6 amps total, we also know that this one resistor wired in series that is connected to them has the same current because this is in series. Okay, so we're dealing with a series circuit, so I'm going to label it S for series. We also know that we want to find our power, or our wattage. So in this case, I'm going to write that P with the underlines and a question mark. That's what we're solving for. I also know we actually already have our I total, which I explained is the same for the resistor wired in series, connected to the section of resistors wired in parallel that we know the total current for. Next, we have a resistance, and we're only dealing with one, so we know that's 10. So now let's think of a formula that has P, I, and R in it. Remember I mentioned the one Peter, Pi squared R. You can always double check that if that helps you at all. Okay, so P equals I squared times R. We know our total current is 6, so we do 6 squared times R, and we know our resistance is that one resistor, 10 ohms. So now we have 10, probably is good to actually label this so you know what you're doing. So we have 10R, and we have 6 squared, which is I, and that simply equals P. So now let's do that. Of course, when you're multiplying, you're just doing a number times itself, so you could just do 6 times 6. Or if you have a square button, like I do on my calculator, you just do 6 squared. We get 36. Of course, we could all do this in our head probably, but I always use my calculator, except if I'm dealing with something like the number 10, which is very obvious. So I could do 36 times 10 equals 360. The reason why I'd only do it for 10 is because you could obviously just look at that, okay, 36 times 10. You could easily double check it. I like to even double check other things like my calculator. Okay, 6 squared. And yes, it was 6 originally. Okay, so it's good to double check things because if you did make a mistake, you're going to catch it when you double check it. Now we have 360, which actually is our wattage. Okay, so the next one may be sort of a review. It doesn't actually have a mixture of series and parallel. So let's do this rather quickly. What is the total wattage of the circuit? Okay, so we see it as wired in parallel, so I'll write down the P. Next, I know we want to actually get the wattage, so I'm actually going to write a P with the underline with a question mark. That's what we want. And we do see a labeled voltage, so we have an E. And we also have resistances of the resistors, so we have R. Now we actually already have E total, which is 120. Okay, so that's already solved for. In essence, we want the wattage of the circuit, so we want the power total, the wattage total. So since we want the wattage of the circuit, we want to find the total wattage or the total power, same thing. The resistances on each of your resistors are going to be different than your total resistance. In a series circuit, since they add together, your total resistance is always going to, of course, be a bigger number than your individual resistances on your resistors. However, in a parallel circuit, since you do the weird thing known as the reciprocal, which you do 1 over each of the resistances, and then you take the reciprocal of that by doing 1 over the total of all that, in fact, now you will actually have a smaller total resistance than you will have on each of your separate resistors. Something good to note, you can double check that. Okay, is the total resistance a smaller number than the two actual resistors if they're wired in parallel? Something to double check. There's also a formula that you can use if you only have 2 resistors wired in parallel. So look that up if you're curious. But I always like to do the same thing. So I'm just going to do it the old school way or the regular way. So do 1 over 30 plus 1 over 40. Of course, these are the resistances of the resistors wired in parallel. Okay? That's going to equal that number, which we're going to do 1 over, and that's going to equal our total. So let's get into it. 1 over 30 equals 0.03 repeating. 0.03 repeating plus 1 over 40, which is going to equal 0.025. In this case, I think we're just going to use the numbers how they are. So I'm going to do 0.03 plus 0.025. Okay, I'm going to get 0.055. But remember, that is just our total of these, which we still have to do 1 over. So now 1 over 0.055, and we get 18.18 repeating. 18.18 repeating. The line over it says that both the numbers are repeating. So now I have the resistance total, and I have the voltage total, which was already given to us. But if we think a little bit, we know that we also know each of these resistors has 120 volts going through it because it's wired in parallel. Therefore, the voltage stays the same. Okay, so now that we have those, we need to think of a formula that has P, E, and R. And we could think of that last one that I called E per with the E squared P times R. So write that down, E squared P times R. So now I know if I want to find P, I'm going to do E squared over R. Okay, so E squared over R equals P. I know that my E is 120. So I'm going to do 120 squared divided by my R, which I know is 18.18. Repeating, but in this case I'm just going to do 18.18, at least to begin with. Okay, now let's do this, and then we'll come up with the answer, and then I'll show you a possibly better way to solve this now that we did it this way. Okay, so we do 120 squared. It's going to be 14,400. And we're going to divide that by 18.18. We might just call it 18. So let's first just do 18. So do 14,400 divided by 18, and I'm going to get 800. Okay, so I have 800, and if I did divide it by 18.18, I would have 792.079. So we can see it's probably not a favorite answer, but I'll at least write down 792. But let's comprehend one thing, and that is that we already had whole numbers to begin with when we looked at our resistors that were wired in parallel. And to get our total resistance, we had to do the reciprocal. And of course, that kind of takes a little while to do that. And you can see that basically took up a whole page doing that. So it's good to know that you don't always have to solve for your total resistance. And because we already had whole numbers to begin with, to get the more accurate answer, here's going to be a method that'll probably work better. So again, we're working with a parallel circuit, so I'll write the P and I'll circle that. We want to find the power, so I'll write the question mark and I'll underline that. We have the voltage, and we also have resistances. We also already know that the total voltage is 120 volts, and we know we have two resistors. We have 30 ohms and we have 40 ohms. Okay? Now think of the same formula. I have P, E, and R. So E squared is P times R. And since I want power, I'm just going to do E squared over R. So this is how I'm going to do it. I'm going to think 120 squared over 30 equals one number. Then I'm going to think 120 squared over 40 equals another number. Those two numbers, I'm going to add them together, and that will create my total power. Since like I explained in my series versus parallel circuit video, whether you're in series or parallel, it doesn't matter. You can figure out the individual power of each of your resistors, add them together to find your total power. Okay, so let's first identify 120 squared. And of course, we just did that, and it was 14,400. So now 14,400 divided by 30, and we have 480. Then we do 14,400 divided by 40, and we have 360. Now we're just going to add both of those numbers together. Okay, so now you can see we got the answer 840 for our power total. Now if we compare that to what we did originally when we solved for the total resistance, and then we used that number, we had either 800 using the rounded number, or using the original number, we had 792. So no matter if we use this number or if we add more of the repeating 18s, we're just going to have either one of these numbers or land somewhere in the middle. Well, here we can see we have 840, which is 40 above 800, which was the largest, and percentage-wise, that's quite a large percent. So you can see that just because we have a parallel circuit and we have two different resistors and we want to find the total wattage, that doesn't mean, okay, just find your total resistance. In fact, we can actually see we got the more accurate answer, keeping the whole numbers of the resistances, and then separately finding out the power for each of them and adding those powers together. So this is one of those things where you got to know a certain time and place where you should use a certain method over a different method. In this case, avoiding solving for the total resistance actually saves a lot of time, and we can see we only took up about half a page versus before we took up about a whole page doing the same problem and not getting as accurate of an answer, plus a lot more math. Okay, moving on to the next one, we see a mixed circuit now where we see a resistor wired in series, and then we again see 3 wired in parallel. We might see the same numbers, but we're not asking for the same thing. Okay, so again, each of the 6 ohm loads has 2 amps. And the question is, what is the voltage drop across the 10 ohm load? So that's a funny thing. They throw a lot of words in here when they ask the voltage drop across the 10 ohm load. They're asking how much voltage is going to be used through that 10 ohm load. So that would be known as the voltage drop because it's going to be subtracting from the total voltage. And that is because you add your voltages in a series circuit to create your total voltage. So that chunk of it is going to be taken away from the total voltage. Okay, so we need to look at some things. We're looking for the voltage drop across the 10 ohm load. We see the 10 ohm load is wired in series. Okay, we had similar numbers, but we're going to think fresh each time. We want to find voltage, and the information that we have is each of the resistors, resistances, and then the load going through each of the 6 ohm resistances wired in parallel. Okay, so now we know if we have a total current of our 3 resistors wired in parallel, since that section is connected to this resistor that's wired in series, then we know that they're going to share the same current. So to figure out the current going through this resistor, all that we have to do is find out the total current for these 3 resistors wired in parallel, which we already have the current for each of them. Again, like I explained in my series versus parallel circuit video, when you have circuits that are wired in parallel, you're going to be adding the current together. So because I'm doing a parallel circuit for this section, I'm going to write that P with the circle. We also know that we want the current total, so I'm going to write that I total. And since each of the currents is 2, and we add them together in a parallel circuit, our total current is 6. Okay, so now we have total current, and we also have an I, and then we already had the resistor that we're solving for, so we have an R, and we're looking for the voltage, so we're looking for that E, so again I'll do the question mark in the line under it, so we know that's what we're looking for. The resistor's just 10 ohms, so I can just label that under the R. So now I know the 2 numbers that I'm going to be dealing with. So what formula has I, R, and E? It is the one that I call EAR, which is E equals I times R. Okay, so we're looking for I times R. So we're looking for 6 times 10. Okay, so now we know the voltage going across this resistor wired in series. And now the next question is, what is the total voltage of the entire circuit? Okay, so now when figuring out the total voltage, we have to ask ourselves a question. Since in a series circuit we're going to be adding voltages to create our total voltage, should we get our separate voltages and add them together? Or since the resistances add together in a series circuit, should we find the total resistance for our parallel circuit and then add that to the resistor wired in series and get the total resistance and then find the voltage for the total resistance? Okay, so let's just quickly do both and we'll figure out which one is better. First, I'll add them together. So we already know that we solved for our series circuit. We know that the voltage going across that, the voltage drop, is going to be 60 volts. So we already have that. Now we need to find the voltage going across the parallel circuit. And since the voltage stays the same for each of the resistors wired in parallel, then we're actually just going to want to solve for one of these, and then it'll tell the voltage for all of these. Okay, without getting the total resistance, because we already have the resistances for each of the resistors. That's the number we're going to be using. Okay, so we want voltage, so we want E. We have resistors and resistances, so we have R. We also know the current, so we have I. We're dealing with a 6 ohm resistor that has 2 amps of current, because we're dealing with the individual one. Now to find the voltage of that, we need a formula that has this. Again, we're going to use EAR. E is I times R, so we're simply going to be doing 2 times 6, and of course that is going to equal 12. That is going to be the voltage for the parallel section of the circuit. And now we know all of the voltages for the parallel section of the circuit, since in parallel circuits, all the voltages remain the same. So now we know each one of these resistors has 12 volts going across it. Since we also know that this is connected to this resistor that's wired in series, then these voltages are going to add together. We already know that the 10 ohm resistor has 60 volts, and each of these have 12, which altogether they're the same, so it's just 12 altogether. So 60 plus 12, and we come up with the number 82. Okay? So we have 82 total volts for this circuit. So we can already see that came up with what looks like the better answer. We have all whole numbers, we're not dealing with a bunch of decimal points, and this is because we didn't get that total resistance. If we get the total resistance, we're probably going to be dealing with some decimal points. So you got to know the time and place when you're going to want to find your total resistance. The main time that's going to be is when they're asking for the total resistance. But however, in this case, you can see that when we're working with resistors that are wired in parallel, keeping the individual whole numbers by themselves without creating the total resistance not only makes this easier with less math, but makes the actual answer a simpler number, which is most of the time more accurate as well. So it all works out very well. We can see that did not take up very much space. So now, of course, you can skip this part, but I'm going to show you what happens if we instead do the reciprocal and try to do the same thing. And when I say reciprocal, I'm referring to that resistance total, because you're getting the reciprocal of each of the resistances, which is 1 over each of them, and then you're getting 1 over that. The reason why it's called a reciprocal, just a very simple math lesson, is because any number is over 1. 20 is over 1. So to get the reciprocal of any number, you're just flipping that. So the reciprocal of 20 is 1 over 20. That's what I mean when we're doing the reciprocal. Okay, same question. What is the total voltage? Okay, to make this quick, I'll transfer some of the stuff from my last one, like we had the voltage total, the 60E. Okay, so we're looking for the voltage total. We have resistors, and we have current. We already know, like we're going to think the answer before that, we have the 60 volts, and that is from that resistor that is wired in series. Okay, so we already know 60 volts, and we also know a total current, because of course the total current was just 2 plus 2 plus 2, we got 6. Okay, so I'm trying to make this a little quicker since I kind of already did this. I'm just showing you what happens when you do the reciprocal. So we have 6 I total. Of course, since this is wired in series and it's connected to these wired in parallel, this total current is going to be the same as this. I know I keep saying that, but it's good to really repeat these things. So we have 6 amps through everything. And now I'm going to try to find that R total. So I'm going to do the 1 over 6 plus 1 over 6 plus 1 over 6. I'm going to get that total number, and I'm going to do 1 over that number. So as you can see, we're already starting to write down almost equivalent to what we had before, and we're just starting. So it's just the fact, too, that getting total resistance takes time. Okay, so again, 1 over 6, we're going to get 0.16 repeating. So I'm going to keep the numbers as small as possible for this example. 0.16 plus 0.16 plus 0.16 equals 0.48. 1 over 0.48, we have 2.083 repeating. Okay, and there's where we have that decimal point number now. So now we finally have the resistance total after doing all that, and now we have 2.083, kind of a weird number because it's basically 2, but you have a little bit of something there. And now remember, we're using the E equals I times R, what I call ear. So I times R, we'll do 6 times 2, we'll get the number 12. And of course we could have added those numbers, but it's such a small number that I'm thinking that of course we're going to be rounding down with the 0.083. It could be 2.1 technically, but I'm assuming we're just going to use the number 2. So we have 6 times 2, we have the number 12. And of course that is that voltage for the section of resistors wired in parallel. And since that's connected to the resistor wired in series, the total voltage from these resistors wired in parallel is going to add to this voltage going through this resistor connected to it in series. Therefore, we're going to get 60 plus 12. When we get 60 plus 12, we have 82. So as you can see in this case, we got the same exact answer. The only difference is how much room it took and how much time it took. This took a lot more time to get this answer, And I even translated some stuff from the beginning. And we can see the other one, this little section was actually just the answer for the other one. So that's why oftentimes if you're able to use the whole numbers of each of your resistors that are going to be wired in parallel versus getting that total resistance and using that number, you can see you don't only save time, but you have the possibility of getting a more accurate answer, as we saw in an example earlier in this video. Okay, now moving on to circuits that have a mixture of series and parallel, but now we have some switches in there as well. Nothing too complex here, but it's basically just the introduction of, okay, sometimes we're going to see switches in a circuit as well. Okay, so the question asks if 6 amps flows through the 10 ohm resistor with all these switches open, the voltage between terminals X and Y is how many volts? So we see the 10 ohm resistor right here, and it's saying there's 6 amps flowing through it with all these switches open. Then now we also want to know the voltage between terminals X and Y, which we can see is the beginning and end of this circuit, so we want to know the total voltage. So that's where they're asking in many different ways and using different terms for the same thing. Okay, and since this is a beginning one, it's going to be pretty easy. So let's look at the circuit. We see some switches open, and it's saying all the switches open in the question, so that's what we're looking at. And we can see, in fact, that if we follow each of the resistors, so the first one, we can see it's wired in series because what would be wired in parallel, that switch is open. And then it's wired in series to that other 10 ohm resistor that's in series. And then since we have some more switches open, we would have parallel circuits here, but in fact we don't. We just have another circuit wired in series. So we actually just see 3 different resistors wired in series, but with some switches open. Okay, so now let's write that down. We have a series circuit, so I'm going to write S. In this case, I'm going to write down what I have at the moment. So I have a 20 ohm resistor, I have a 10 ohm resistor, and I have a 40 ohm resistor. And I also know that 6 amps flows through the 10 ohm resistor. So I can write 6 amps, or let's do 6I. And again, that is with all these switches open, which is what we're looking at here. And now we simply need to just understand series versus parallel circuits. So we think about current in a series circuit. We know that current's going to stay the same while voltage is going to add. Since we're dealing with current, now we can label all of these as 6 amps because they're all wired in series to one another. So they're all going to share the same current. And next we're looking for volts, so there I labeled that. Okay, so let's just first think of the formula we're going to be using. We want E, or volts, and we have current, or I, and we also have resistance, so R. And now, same formula as before, we have E, I, and R, so we're going to do E equals I times R, what I call ear. Okay, so we have E equals I times R, so I, of course, it's staying the same in a series circuit, so we have that constant 6 amps is our I, and that's going to be multiplied by our resistance. Now, we need to realize we're using a series circuit here. So we could get each of these separate voltages and then add them together, since in a series circuit you're going to be adding your voltages together, or since your resistances just add together in a series circuit, in fact, we're going to come up with the same exact answer either way, versus before in the parallel circuit when we were solving the total resistance in a parallel circuit, we oftentimes come up with an answer that has a decimal point and sometimes can throw off the accuracy of what we're looking for versus if we don't find that total resistance. So in this case, we have a series circuit. There's not going to be a weird decimal point number from adding whole numbers together. So in this case, it won't make a difference, and it'll probably be easier if we just add the resistances together in the first place. We have 40, 20, and 10. I don't think we need a calculator for that. We have 70 ohms right there, adding all those together. So I'll do 6 amps times 70 total resistance, and these are both total, so I could just write T next to both of them. And then I could do 6 times 70, which, funny enough, is 420, but let me do it on the calculator, because that's better. And we see that 6 times 70, we have 420, so now we kind of just double check that. And that is the E total. Okay, so we see this one's pretty simple. With all the switches open and everything was just wired in series. But something simple like this will now get us thinking, okay, we could be looking at something with switches. What'll happen if we start closing switches? What happens if we deal with a circuit that has a certain value with open switches, and then now we want to find a certain or total value with the switches now being closed, which is definitely a real life scenario. So it's definitely good brain food to start with something like this at least. And now we know the total voltage between terminals X and Y. And next, before moving on, we can see that if we did get the separate resistances of each one, instead of adding them together, we in fact get the same exact answer, since we're just adding the resistances and we're not doing that weird formula with the parallel circuits. Okay, so this next one doesn't have switches, but I think it's a good time to put this in here. And that is asking the total wattage of this circuit. So we see the 10 ohm resistor in series with 3 6 ohm resistors wired in parallel. And we have the information that each of the 6 ohm loads is each 2 amps. Okay, so since this is wired in series and these are parallel, and we do see that we have the labeled current, let's at least figure that out. Since the resistor that's wired in series to the 3 that are wired in parallel are going to equal the same current. Okay, so first for the parallel section, I'll just write the P. I have 2 plus 2 plus 2, and that equals my total current. And again, that's also my current now for this 10 ohm resistor. So that also means if I knew originally that this had 10 amps going through it, and I didn't know what these had, since these are wired in parallel to this, and these all three have the same resistance, I could have very well just gotten this number and divided it by 3, since these are all going to add together to equal this. Okay, so that's just good things to comprehend. And now we want to find the total wattage. So what we're looking for is wattage or power. Okay, we definitely have resistances, and now we have not only current of the one resistor, but of also the 3 that are wired in series, what they are separately and what they are added together. Okay, so now what formula could we use for P, R, and I? Of course, we could do P is I squared times R. The only problem is sometimes we seem to be running into some problems when we do the resistance total. So when you stop and think, okay, we're doing the wattage, we're solving for wattage, would this be a good time to do the resistance total? Maybe we could find a formula that doesn't include the resistances, but still includes current to get power. And of course, process of elimination, that would have to be voltage. Okay, so formula has E, I, and P, and of course that would just be the simple formula, P, I, E. Pi is a funny way to remember it, but the better way to remember is that it's current times volts equals watts. Okay, so we know we're going to be first going with this formula. P is I squared times R. Let's first write down some things. First, we already have one of our resistors that is in series, and that is 10 ohms. Label that with an S. And now we want to find the resistance total of this parallel section of the circuit. So again, for that, we're going to have to do 1 over 6 plus 1 over 6 plus 1 over 6 equals that total number, and then 1 over that total number. That's going to equal our total resistance of that parallel section of the circuit. 1 over 6, we get 0.16 repeating. 0.16 plus 0.16 plus 0.6, again, we have 0.48. So now we do 1 over 0.48, and we get 2.083. And that 3 is repeating. That is our R total. And that's just for the parallel section, though. So now to actually get the R total of the entire circuit, we're going to add those two together. Let's just keep the number 2 instead of doing 2.083. So we'll just do 10 plus 2, and we all know that equals the number 12. That is our actual R total of the entire circuit. So for this one, I'll actually write RP, because it's more like the resistance of the parallel section. Okay, now we have R total. Now we know we just need to do I squared times R. Since this is wired in series, that's going to be the same as the resistor that's wired in series connected to it, which is a total of 6 amps. So we get that 6 amps, we square it. I squared. We multiply it by our resistance total, which we now figured out is 12. So now we have 36 times 12. 6 squared is 36. And we can see 36 times 12 is 432. And that is the answer that we are looking for, 432. Okay, so now let's do the same thing, but instead choose pi instead and use voltage instead of using resistance, so we avoid doing the whole total resistance thing. Now we're going to have to find the total voltage though. Okay, so I transferred the simple information that we have an I total of 6 amps, and now we're looking for that E total. Okay, now we just need to think about the fact that if we have a parallel circuit, that our voltages are actually going to stay the same. While if we have a series circuit, it's going to add the voltages, while the current will stay the same in a series circuit. So with the information, let's figure out the voltage of one of these resistors that is wired parallel, and that'll tell us the voltage of all of them. So we have 2I going through each one, and those are 6 ohm resistors. Okay, so we know we have I and we have R now. So we need to form with EI and R. So again, we have the E is I times R. So we're simply going to do 2 times 6, which we know equals 12. That is the voltage of that parallel section, so I'll write EP because we know that in a parallel circuit, again, they share the same voltages, so now we know each one of these 6 ohm resistors has 12 volts going through it. Now we need to comprehend that if we have stuff wired in series, that the voltages are going to add. And since these are all the same voltage, if we add the voltage that we figured out for our parallel section, which is all the same, which again, the total voltage for a parallel circuit would be the same as each one. So we know that this total section of this parallel circuit is going to have those 12 volts. If we add that to this section of the series circuit, if we math out these volts, then we're going to have our total voltage. Okay, now here we have 10 ohms of resistance, and we actually know our resistance of this is going to be 6 because that was our I total, or the current that's flowing through this series section of the circuit, as well as the total current going through this parallel section of the circuit. So again, we have E equals I times R. 6 times 10, we're going to get 60. So of course that equals E of the series section, and now we have to do 60 plus 12. And we see that now we get the answer 82. And now we have the E total. Okay, but now we know that the whole point of this is that we wanted to find the power though. So we just did all that to finally find the E total. Now we still need to find the power. So you can already see where this is not as good as the last method. So to find P, we're going to do pi. We want P equals I times E. So I times E. We have a total of 6 amps of current times a total of 82 volts. So this time, not doing the total resistance actually caused a lot more solving, since we actually had to solve for a whole new thing, the voltage. Now we had to find out the voltage of everything, instead of just finding out and adding up the total resistance of this parallel section. We in fact went into a whole new formula, which ended up actually causing some more math, some more time, and room. Okay, next we have a circuit with switches and a bunch of resistors. Some are wired in series, some are wired in parallel, and it also depends how the switches are open or closed. The question is, if line current is 10 amps with all of these switches closed, the circuit consumes how many watts of power? Okay, so now this is an interesting question. I don't think it's a bad idea to solve this, but we need to think about the mindset of being on a test and having limited time. This is probably going to take a little while, and it's not the most straightforward question either. I can't actually figure out if they're asking if I'm supposed to solve for the circuit with the switches open, or if I'm supposed to solve for the switches with it closed. That's not very clear to me, actually. Furthermore, to solve this correctly would already take enough time, so if I actually did it incorrectly the first time, then had to do the second method, that would eat up a lot of time that I could possibly getting a better percentage by scoring more correct answers on the test. So I think this is a good example because depending on how much time you have during the test tells you if this would actually be probably a good idea or not. So my challenge for the video is for you to solve that and to give me the answer in the comments. But my advice is that you have limited time when you're taking the actual test. This is going to take a while to solve. You have some options here, and this is my advice. One would be make a good guess and move on, or two, come back later when you solved other less time-consuming questions. So it's probably good just to make a good guess before you do that, and you can always come back later if you have more time at the end. Okay, so that's it for this video. If you had any questions, feel free to leave it in the comments. Give the video a thumbs up if you enjoyed it so other people can see this as well. And subscribe to see more videos on electrical theory. I'm going to have a lot more coming out that will help us understand the whole concept of electrical theory. Maybe not electricity, because electricity is very complex, we can all admit, but there is an understanding to the electrical theory. So a lot more videos on that coming out in the future. Simple things like voltage drop formula, things on understanding motors, frequency, the sine wave, trigonometry formulas that then tie into electrical theory, and a lot more coming up. So be sure to look out for those. Until next time, take care, goodbye.